And these tools work very well in certain cases. We want to find out when can we use a particular machine learning algorithm, or when we can use a certain classification algorithm based on the type of data, based on the need, based on the computational resources that are available. And the one typical assumption that is made is that we have this data set, or we have these models that are Gaussian distribution. So we have Gaussian distribution. And Gaussian distribution, in case if you want to see, that is a classic normal distribution. And the two important parameters that describe this distribution is the mean and the standard deviation. So basically sigma. And many a times what happens is a technique which is called as the finite mixture models. So basically finite mixture model that assumes that one or two type of distributions are present in the data set. So, and again, what we do is we actually combine these finite mixture models, and then if the mixture is assumed to be Gaussian, then you get something called as the Gaussian mixture models. And you'll see this word used a lot, which is called GMM. And what that means is you can have one or more Gaussian processes that kind of add up, or they interact with each other and give you the overall distribution. So basically you have data set with one or more mixtures, or more, so basically when I say mixtures or distributions. And then again, as we talked about, that each and every distribution will have its own mean and will also have its own standard deviation. But the good news is these types of distributions, which are combinations of one or more, they are easier to handle than some non-standard, non-normal distributions. So what this algorithm does is algorithm computes maximum likelihood. So the algorithm that we are going to talk about, which is mixture model, and the algorithm that is used to perform unsupervised learning on mixture models, it's called as expectation maximization algorithm. So it's also called as EM algorithm. And EM algorithm is designed. So what this expectation maximization algorithm does, so this EM algorithm is designed to find, so designed to find maximum likelihood parameters you have to find maximum likelihood parameters for statistical models. And then again, if you're a hardcore probabilistic theory, information theory, or statistical analysis, you can actually take an entire course on these different models and their applications. But the idea is this likelihood is a fundamental concept in probability. So if you take probability theory, they will talk about this likelihood all the time. Now, the thing here is this algorithm basically tries to find out the parameters, and it is important to understand that these parameters cannot be directly found out. So what needs to happen is, since you cannot find these parameters directly, you are going to use some type of iterative technique that would actually get you some results. The problem there is, since we are using an iteration, there is no guarantee that it will converge. So what we do is basically we try with start with a probability density function. Xj stands for the random variable distribution, and basically it's sort of the weighted sum. And then you have P is equal to 1 to K. You have alpha P, Fp, Xj, theta P. And you will notice this, that this F is actually called as the probability distribution function. And this PDF, which is on the left hand side, is the overall probability distribution function. Now, what we do is we want to find out this parameter theta. So this needs to be found out. So in order to get the estimate of this parameter, to get estimate of parameter, we use something called as the Fisher's estimate, which is called as maximum likelihood estimate. So this is used, maximum likelihood estimate. And this is basically you take the roots of partial L, which is function of theta, partial theta is equal to 0. So you can think about this like an optimization type of approach, where you take the partial derivative of this L function, and this L function is nothing but the summation of the logarithm of the probability distribution function. So basically J is equal to 1 to n. So log of f x of j given theta. Now again, this is an iterative problem. So you're going to start with one guess, just like any other optimization problem. You're going to solve with one guess, and you are going to proceed to the second guess, and then basically update the guess, and then try to see if you can get, if at all you can get some solution somewhere. But please understand, there is no guarantee that you will get the solution, but there is most likelihood that if you start at the right iteration, or if you start with the right estimate, or if you start with the right guess, then there is a strong possibility that you may be able to reach out to the estimate. Now, another thing which I want to talk to you about is what are the applications? So the applications is something like this. And I will show you the example, a concrete example in a minute. But what I want to show you is, imagine you have a mixture, like you have cats and dogs. And what we want to do is we want to look at uh, basically where are uh, the cats clustered, or where is the data associated with cats clustered, and where is the data associated with the dogs clustered. So what we can do is, imagine if you have this distribution and you can use some type of a principal component, or what you can do is basically you state that I'm going to use the first singular value decomposition vector, or second singular value decomposition vector, or I use the principal component analysis, say first principal component analysis, or second or fourth, whatever. So you get PCA 1 and say you have this PCA 4. And then what you do is you have this distribution. If you have this distribution, what this Gaussian mixture model will do is this will actually, depending upon how this whole thing is distributed, it will actually fit the distribution lines. It will actually cluster these together. And again, for that, what I'm going to do is once I discuss the theory a little bit, then I'm going to actually show you the examples, wherein what you will observe is, in the last class we looked at the dogs distribution and cats. When they are mixed together, you see some clusters. But then what this GMM technique or this algorithm would do is it will actually separate out those two independent distributions. So you can actually see the distributions correctly. And I will actually show you how that works a bit later today. So this is called as the Gaussian mixture model. And again, what we are looking at is we are looking at unsupervised learning. So which means we just have this data set, and what we are going to do is we are going to use this data set, and then we will let the algorithm decide which pattern emerges. Now, the next thing which I want to talk about is, if you were to go to the supervised learning, in supervised learning, what you have is you have labels. So basically, you know for the fact whether this data belongs to cat or this data belongs to dog. And then what you want to do is you want to discriminate, or you need to find out the difference between those two data sets. So that is something, the most important undertaking of supervised learning. So before we started doing neural networks, deep learning, a workhorse for supervised learning was something called as LDA. So LDA, it's a statistical approach, and this is actually linear discriminant analysis. So LDA, and it's a statistical technique. The idea here is this approach tries to solve an optimization problem. So the algorithm is trying to solve an optimization problem wherein uh, basically the embedding its embedding is easier to observe. So what that means is you are actually to find embedding. Now embedding, in case if you are wondering what embedding means the hidden structure in data set. And then the classic approach is you have this data set. This data would have the actually the trained data, and you would have a test data. And basically LDA or any type of supervised learning is trained on this training data set, and then whatever the classification boundaries or differentiation, whatever you get or pattern that is tested, so you actually get result, and this actually used onto test data, and then you perform the verification that is actually good. Now so again, this is something that is very important. Now let me try to explain what exactly happens in the case of linear discriminant analysis. So imagine that you have a data set wherein you have let me show it something this, like you have two different data set, like you have a cat, and then what you have is you have the dog. Now what I want you to do is I want you to use this coordinate for classification. So basically what I want to say is I want to find out maybe one of the features of the cats and dogs. Say for an example, maybe the length of the feet, or maybe the weight. So there is some feature here, like which is I'm just gonna say weight. And if I try to classify this, so if I were to find out the distribution or the projection of the cats, and if I were to find out the projection of dogs, then clearly you can see that these data sets are sort of mixed. So you have this data set that is spread on this weight line. So there is no clear distribution. So there is no clear differentiation. But as soon as I use some other parameter, maybe the other parameter could be the height. So height. And assuming cats are short and are tiny and dogs are tall, you have very clear distribution between these two data sets. Now you have the first line of algorithm or some type of differentiation, whether you see these two different patterns. And again, this is a statistical problem. So the idea here is, and again, I want to tell you this, and I kind of told this early in my earlier classes, that when we are trying to analyze the solar system, when we assume the Earth to be at the center of the solar system, then we got some weird, I mean, not very uniform orbits of the planets. So basically, these planets were orbiting. So when we looked at the Earth center solar system, these orbits were like this. So this is Earth center. But Kepler, what he did, he derived the same orbits again experimentally. He actually looked at the experimental data, a lot of experimental data, and then he looked at the sun-centered or heliocentric uh, the model. Then these orbits were fairly uniform and decent. What that means is depending upon what glasses that you choose, depending upon uh, the, the the projection vectors that you choose, depending upon the coordinate system you use, you'd be able to find the structure in the data. Now, what does that mean in terms of an actual algorithm? So in the actual algorithm, if you think about it, is basically you try to find out. So we are trying to construct a projection W. So W is the projection. We are trying to construct the projection such a way that we have arc max. We are trying to maximize the separation between the data set. So you have W. So what this means, and mathematically what this means is I'm trying to maximize the distance between these two data sets. And how it is done is basically we use a computer software or we use some type of algorithm logic to do this. But the idea is if you have the distribution, then we are trying to find out a line that maximizes the distance between these two data points or these two classes of data. So we are going to maximize the distance that separates out this. And MATLAB is very efficient in doing this. And there is basically a linear discriminant analysis type of function that we will talk about very quickly towards once our discussions are done. But MATLAB is very, very effective and efficient in performing linear discriminant type of analysis. Now, next thing is, does LDA, do we LDA, when we use LDA, we can use a straight line for differentiation. Sometimes the straight line may not be the best possible way to separate out these two data sets. So for an example, you can have a data set wherein your data set is like this. So perhaps what we can do is we can fit a curve that actually separates out the data set. So again, depending upon whether you use a line, whether you use a curve, what type of equation that you are dealing with, that would tell you whether you have a linear discrimination between two, or if you have some type of a quadratic equation that is separating out these two individual distributions. The next part, and I'm going to solve the MATLAB problems. I'll show you the MATLAB codes and we will actually discuss how to do it. But rather than going back and forth, let me just explain all the techniques, and then I will walk you through the codes. So the next technique for supervised learning is, the first technique is linear discriminant analysis. The second technique is support vector machines. So in support vector machines, what we are going to do is this technique is used successfully for data mining, small scale data mining, even large scale data mining. So if you want to mine data, SVM is actually used. SVM took place basically in 1930s. So let's start with the approach here. What is the linear SVM? So there is a linear SVM. The idea of the linear SVM is we want to construct a hyperplane. So the idea is a hyperplane. So in hyperplane, what we have is we have W x plus b is equal to 0, where you have W and you have this b. They are the parameters of hyperplane. And the idea is we want to find out these two hyperplanes so that we have some type of discrimination. And again, if you look at the actual approach where this hyperplane is constructed, what we do is we cast this problem as an optimization problem. And that's why machine learning is closely related to optimization. So it's like we are trying to formulate this problem like an optimization problem. So in optimization problem, what we are trying to do is whenever you look at optimization, the way the optimization works in very simple terms is you create some type of a function, and sometimes it is called as the loss function, sometimes it's called as the cost function. So what you do is you have this function, and what we want to do is we want to minimize or maximize. If you want to maximize, you take a negative. You want to minimize or maximize this loss function or cost function. So if you look at this, this is written as argmin, which means we have to minimize the arguments to find W and B such that for J is equal to 1 to M, you have L Yj and Y bar J. So these are the two different data sets wherein you have some type of a penalty or correction function which is given over here, subject to minimum J, where you have Xj W is equal to 1. So this is mathematical representation of determination of these parameters W and B, so that you can construct this hyperplane that can actually come up with the differentiation between the data sets. And if you look at what happens is this guy is associated with the label. So this actually an indicative of label, which means you can say that L Yj Y bar J is equal to 0 if data incorrectly labeled, or you can say +1 if data So I'm sorry, yeah, it could actually change. So I would say this 0 means data correctly labeled, or data incorrectly labeled. And sometimes what you want to do is you don't want to do a crisp optimization, which means you don't want the loss function to be crisp. In a sense, when I say crisp, I'm not saying that would be something like this. So you don't want the function to be crisp. What you want to do is you want to somehow, just like if you look at the activation functions that are used in neural networks, so you want to add some type of smoothing, because you don't want the transition to be sudden, you want the transition to be smooth. So what happens is, to solve this optimization, they use a common formulation which is called as, basically instead of doing this, solving this optimization problem, the problem that is solved is argmin w comma b j is equal to 1 to m, and you use this something called as hinge loss function. And I will explain to you in just a minute what is this hinge loss function. So this is subject to minimum j xj dot w equal to 1, and where this hinge loss function for h yg y bar g is equal to max 0 1 minus yi y bar g. This is called as the hinge loss function. And it basically, this hinge loss function actually allows the algorithm to work on sort of the piecewise differentiation, so that you can actually get results and those results kind of converge quickly. A slight variation of that is, instead of linear SVM, you can use something called as nonlinear SVM. So nonlinear SVM is nonlinear support vector machine. The problem with linear SVM is the data that we deal with most of the times is not linear. We have nonlinearity. So the data, even though linear functions or linear discrimination or linear SVM, it's good to understand or to use conceptually. For practical purposes, we have to resort to nonlinear technique. So now the idea is, what we do is we take the data and we map that into some type of higher nonlinear dimensional place. So I'll give you an example. So the idea is we map data into, say, higher dimensions. Now, a very simple example is, imagine you have a data set, you have x1, you have x2, and so I'm gonna call this, say you have 3, 4, then you have 5, 8, some type of data set. So if you were to just look at x1 and x2, you may not be able to differentiate the data set. The separation will not be clear. So what I'm gonna do is, I'm gonna construct an additional vector which will comprise of x1, x2, and maybe x1 square plus x2 square. So now what I have is, I have these three parameters to play with. And then it may so happen that when I look at this data set, then I would notice that x1, x2 will get mapped somewhere here, and that the pattern would emerge. And then I would see another pattern, which is somewhere over here. So it may not be very evident looking just at the data set, what is the differentiating factor. But once I look at the derived nonlinear function, which is x1 square plus x2 square, then maybe this pattern would be more visible. The other approach is, imagine that you have this data set, and that data set is kind of spread and mixed. So for an example, you have this data set somewhere here. So you have these red points, and then what you have is you have these green points. And if you look from top, then you will observe that the green data set is somewhere concentrated in this small circle, and this red data set, it kind of concentrated in this larger circle. And this is a very important pattern when you are trying to understand the system. So for an example, very many times when we have a dynamical system, and this is a very practical approach that is used. So for many times, if we have a dynamical system, like a spring mass system, what we do is we look at something called as the phase plane. So you have x and x dot. So what you do is you look at phase plane. And if you look at the phase plane of the system where you have just spring mass system, then you will notice that phase plane is something like this. It's a closed circle. Now imagine if you have a spring mass damper system, you would observe that the phase plane for this system, even though both these systems can start with a similar initial condition, this other system would kind of spiral in. And this pattern could be visible on a plane which is x dot plus x. Alternatively, you can do x dot square plus x square, and this actually gives you sort of the total energy content. So a quick side note. So if you look at this, imagine if you have a spring of K is equal to 1 Newton per meter. And if you have mass M, which is equal to 1 kg, if you want to write down the energy function E, which is nothing but the kinetic energy and potential energy, what you are going to get is you are going to get, just for the sake of discussion, I'm going to write this 1/2. No, I will just write this 1. This is easier, 1. So this kinetic energy is going to be 1/2 multiplied by 1 x dot square. So let me say this 2 to make sense. And then this plus 1/2 2 x square. So this gets cancelled, this gets cancelled, and I get an expression for energy, which is given as x square plus x dot square, which is equal to energy. So what that means is, sometimes if you just look at the displacement, if you just look at the velocity, it may not be evident, but once you look at the energy, you can totally see the system is different. And that is the basis of something called as Lyapunov techniques or Lyapunov approach. And this is a very famous technique in dynamical systems or controls. then what you do is you find the total energy of the system. So you find total energy. And in my robotics 1 and robotics class, I talked about this approach. You find the total energy. And if you observe that your total energy is remaining constant, if your total energy EE is equal to constant, then basically the system is simply stable. So system is oscillatory. Just like our spring mass system, the oscillations are neither increasing nor decreasing. So basically like this. If the total energy is decreasing, then in other words, if you see your total energy as time goes on, the total energy goes down. So you would observe for a spring mass system, the oscillations are decreasing. So you can actually see the exact same pattern here. So here, total energy is decreasing as time goes on. And here, the total energy is remaining constant. Now, depending upon the nonlinear approach that you use, you have different kernels. Now, basically, so this is an interesting observation. So what is a kernel? So kernel methods for SVM. So the kernel method for SVM, yeah, so if you have the system that has damper, so if you have the system that has damper, so what I've shown over here, this is how the system looks. And if you have system, this is how the system looks. So if you have a damper, what damper is going to do is damper is going to absorb some amount of energy in every oscillation. So a classic example is, imagine if you have a spring mass system and you are on Earth and you pull the mass and let that mass oscillate, you will notice after some time, because of the air resistance, the mass comes to a complete stop. But now imagine you take the same spring mass system and put it inside the vacuum and perform the same experiment, pull the mass and let it oscillate. You will notice it will go for a very, very long time. For the practical purposes, it could be for infinite period of time because there is no air resistance. So energy is not dissipated. So that's why Lyapunov approach sometimes will give you global solutions for stability. But coming back to the kernel method for SVM, so the problem here is, remember there is something called as curse of dimensionality. So this is curse of dimensionality. It means as dimensions increase, as dimension increase, the amount of computational power or computational time. So computational power or computational time increases. And the problem is, if you want to find out the kernel vectors, or if you want to find out nothing but the W, or basically the features, if you have few features, they can easily be found out. If you have quite a few, lot of features, realistically, it may not be possible to find out. So what this kernel does, it actually solves this dimensionality problem in a little bit, which means computation problem is sort of becomes tractable. So you have this W is equal to sigma, J is equal to 1 to M alpha J, then phi x of J. And these are the different weights and these are different nonlinear observable functions. So what happens is, this idea is, now if I want to represent the previous formulation f of x, I can rewrite this as J is equal to 1 to M. And this is the exact same equation that we looked at in earlier SVM. So basically, this equation that we talked about. So this equation can be rewritten in a slightly different fashion as alpha j xj p x plus b, and the kernel function xj x is defined as p xj p x. And again, these equations may not sound very exciting, but the idea is, with this kernel, the optimization problem becomes quite easy to solve, which means the optimization problem become argmin alpha beta j is equal to 1 to m. You get h yj y bar j plus 1/2, and this is the change. You get sigma of j is equal to 1 to m alpha j p of xj. Now it may not sound like it, but please trust me when I say this. Solving this problem numerically is easier and can be solved in real time compared to the previous nonlinear SVM problem. So subject to minimum j xj dot w equal to 1. Okay, so if some of you are interested what this kernel is doing, it's basically performing a Taylor series approximation on the large number of observables. And the idea is you can use any kernel. So the typical kernels that are used are radial basis function, and you use polynomial kernel, and depending upon, again, the time, resources, accuracy, what you need, you can choose a particular kernel. And I want to show you an example how these techniques work, because the math may sound boring, but to be honest with you, to use these techniques, we don't really need to know the math in detail. We need to have some type of understanding just to make sure that we are not using the wrong tool to solve the wrong problem. So as long as we have a little bit mathematical understanding, we can decide which classification technique would give us the best possible result in the with available resources. So the last technique which I kind of want to talk about briefly is something called as the classification trees. Trees and random forest. So again, there are additional boosting techniques that can make some of these approaches even better. So basically you can reinitialize, but the idea is you start with something called as a decision tree. So basically you decide whether you want to go this route, that route, if you want to go this route, that route. So you have something called as the decision tree. And this decision tree is sort of the hierarchical structure that actually allows us to kind of classify. Now, how does it work on the real data set? So I want to actually start with this example. Imagine that we have maybe cats, dogs, and rats, something like that. So we have three different data sets, and then you will see the rats are clustered here, and cats are clustered here, and dogs are clustered somewhere here. Now, the way I want to do it is I want to perform some type of classification so that the rats are different from cats, are different from dogs. Now, what I'm going to do is first, I'm going to come up with the decision boundary here. So this is going to be my decision boundary to differentiate or separate out the rats from cats and dogs. So I would say if the data set, maybe the weight, if it is below the decision boundary, that's a rat. If the weight is outside this decision boundary, then we have either cat or dog. Then what I do is I then actually come up with some other type of logic, maybe the length of the animal. So maybe rats are smaller, cats and dogs are bigger. Then what I do is I add additional level of granularity. So what I do is then I say maybe I would add little bit more granularity here. So this is my first decision boundary. My first. This is my second. And then I have this third. So I can sort of classify depending upon which block the data belongs. And I can say if the data is in this block, this is the rat block. If the majority of the data is here, this is the cat block. And if the majority of data is over here, this is the dog block. So this is exactly the mathematical algorithm that is happening. And then what you do is, if you want to construct the tree, the decision tree, you basically do the exact same thing. You partition this and you will have different level of granularities, and then you can construct the decision tree. And MATLAB is actually very efficient in doing this type of analysis. So I will show you an example in just a minute, but the last thing which I want to talk about is something called as the random forest or random decision trees. So these decision trees are kind of structured. So there is a very nice structure to it. So they are deterministic. They are not random. So if you were to do it, if you were to do the repeat the process randomly, that's why it's called as random forest, because you have something called as the decision tree, and now you are doing the whole thing all over again randomly. So that's why now tree becomes forest. So what happens is uh, basically it's an ensemble learning method. So which is learning on the huge data set. So it's an ensemble learning method that is used for classification and basically pattern recognition. So you classify and then basically you perform some type of regression. And random forest itself is a big topic. There are different variants, and MATLAB has the important ones, but the classic uh, random forest techniques are like something called as the boosting and bagging. Now, what that means is you take the data set, perform the analysis, then add some remaining data set, the data set that you already analyzed, and do the classification. Then basically, or you take different samples from the same data set, varying samples, and then perform the analysis. So random forest, again, I would encourage you to take a look at random forest, but I'll show you an example. So if you want to think about over the last decade, uh, there was enormous progress made in the deep learning techniques. But before that, the important tools that engineers used and data scientists used is k-means, then Gaussian mixture models, then support vector machine. Then there is something called as classification and regression tree, CART, classification and regression tree. Then you have something called as KNN. Then you have something called as naive bias, a base. Then there is something called as the ADA boost, which is something like ensemble learning. Then you have something called as C4.5. And please understand this C4.5 is different than C45, that the fitness training gym that you see everywhere. C4.5 is like ensemble learning for decision trees. Then there is something called as the a priori algorithm. And then there is Google PageRank. So these are some of the important algorithms in the history of data science. And believe it or not, all these algorithms, they are based on the techniques in the linear algebra and statistics. So linear algebra is instrumental to enhance these techniques, and basically advances in statistics helped us formulate these algorithms and make them better and use them for our daily applications. Now with that, what I'm going to do now is I'm going to show you the examples on the Gaussian mixture models. I'm going to show you the examples on the LDA. So let me show you what happens